Okay, so your assignment 2 will be released next Monday, early next Monday. So once you submit on Friday, you can review the materials to get ready for assignment 2 on Monday. And then your project for sure will be released by the end of next week, before the reading week. So you got enough time to do both, okay? I'll make a policy clear once we get there, yeah. All right, you're fine, okay. Okay, so let's continue with where we left off from last time, okay. Basically, that's the algorithm that we covered the last time, okay? You're gonna read the details. I'm not gonna bother you with step by step, but we do need to trace it maybe with 1 or 1.5 input just to get a little bit more idea. And then we're gonna talk about other things related to this algorithm here. Okay, so here, basically, there should be an implicit precondition for this algorithm. If you want to do top-down parsing, the grammar you're trying to make reference to cannot be left recursive. Okay, that's basically what we learned from last time. So now, if you review what we said last time, so this is the tracing we did. So given this particular grammar that's actually left recursive, there are actually 2 kinds of left recursion that you should know about. But I'll get to there in just a moment. But apparently this is left recursive because you can see expression here, and the leftmost variable in the production rule is also expression itself. So there's it's called a directly left recursive as opposed to indirectly. But we'll get there. And then we actually said last time this will result into infinite loop. Okay, that's what we learned. What we need to learn today is to see how we can remove left recursion. Let's think about left recursion intuitively before we try to present to you the algorithm. You have to follow certain systematic steps. Okay, let's take a look quickly. Okay, okay, that something will be infinite loop. Okay, that's what we said. And then what we want to do is somehow convert this particular grammar. Okay, I would say for now, just take this grammar for granted, just for now. Okay, let me just make sure my slide is there. Okay, let me just make sure. Sorry. And then we'll get to left recursion in just a moment before we talk about the algorithm. So now consider this particular grammar here. Let's make sure it is not left recursive. How do you check? Basically, check for every production rule, the leftmost symbol. For example, you can see for this particular rule, the leftmost symbol is turn. Is it the same as the left-hand side? Not the same, so that's not left recursive. Okay? But you can take it for granted. So this is the grammar that will actually work for our tracing. Okay, but we're going to talk about how you can go from, for example, this particular grammar, which is left recursive, how we can go from this into the next slides. We'll talk about some algorithm of doing that. But let's just do some tracing first. Let's say, given this particular grammar, but let's get familiar with it first. So I would suggest we try to draw some parse tree, just to get a feel. Okay? I do some comparison for you. Oh, we'll talk about recursion. I'll go back here a little bit later. Okay, bear with me. Let's talk about these 2 grammars. So this is something we said with the left recursion that's going to result in infinite loop. And this is the one I claim which is going to work. We're going to see that. Okay? But let's just try to look at the parse tree quickly. Okay? For this one here, we know very well how to draw it. Okay, let me just put it here. Okay? So now let's say expression, and then you're going to get expression plus turn, and then for expression here, and then it can be factor, oh, sorry, turn, and then factor, and then a. Okay, and then turn can be turn multiply factor, right? And then turn can be factor, and then can be a, and factor can be a. So that's easy. Okay. I'm not going to bother you with that. Can you try to see if you can draw the parse tree for this one here? Okay? Try that with 30 seconds, and then we'll try to put it together. Okay? How about I try to draw now, you also try to draw quickly. This might be a little bit harder for you intuitively to draw the parse tree for. However, it turns out this is the grammar that's going to make the mechanics, the top-down parsing algorithm work. I'll draw that at the same time. Okay, let's take about 30 seconds. Okay, I'll draw that. And notice that the grammar may produce epsilon, which means empty string. Notice that, okay? So guys, at the end of the class, approach me to make sure I take attendance of you. Yeah, just come. Okay. All right, try that. Okay, I'm going to try it at the same time. So turn, expression prime, and then factor, turn prime, and factor over here can just be A, for example. And term prime. Again, somewhere, I hope. Expression prime, and then it's going to be plus turn expression prime. Okay, so now we got plus as well. So now for turn, we can also get factor and then turn prime. Okay, and for factor we can definitely get, okay, and then for turn prime I can definitely try to do the multiplication now. Multiply and then factor and then turn prime. Okay, and then factor I can go into A, and now term prime can definitely be epsilon. Expression prime also can be epsilon. Okay, I would say if you are not doing fast, that's okay. Try to practice on this. My point is, in order for you to do manual derivation, maybe the one with left recursion is much easier. But the point is, if you simply apply the grammar to your algorithm, it's going to run into infinite loop. But the right-hand side with the right recursion, it turns out to be straightforward for the algorithm to apply. We're going to see that picture in a moment. Okay, so this particular parse tree, if you double check with it, you can see A plus A multiply A. Okay, so now one thing I want to note to you. Apparently the structure of the tree simply don't look the same. However, can we argue that the meaning have not changed? Can we argue that? Well, what I meant was, you can see over here, when you talk about this particular A plus A times A, okay, which will be evaluated first? A times A, how do I know that? You can see A times A over here belongs to this particular subtree. So if I want to evaluate them, I want to evaluate the right subtree and then say plus A. So this is how I can see the meaning. On the other hand, is the same meaning preserved on the right-hand side? Yes, just in a way that's a little bit detour, right? You can see this particular this particular subtree tells me multiply by A, right? Well, or you can say this particular one. A multiplied by A, I got to evaluate that first and then say plus and then A. Okay, in some way the meaning is preserved. So I just want to say these two subtrees, even though they look the same, even though they look different, but semantically preserving. That means anytime if you want to pass your grammar to the algorithm, if your grammar has some left recursion, you have to change that to 1 with the right recursions only. And then you can pass that without any infinite loop. Of course, you want to make sure the semantics is preserved. Okay, any question about this? We want to get some intuition first. Okay? Yes?
Do we pass the left recursion to some tool and then the right recursion, or we have to do it?
Exactly true. You can think about, okay, how about this? Well, Mahu's concern was this. How do we go from left to right? You can think about there will be some algorithm to go from this guy here to this guy. There will be some algorithm that we talk about today. Yes, indeed.
Is there not an algorithm that we can use on the left recursion? Because for this specific example, like the tree is almost 1.5 times larger than the number of nodes.
Oh, you mean on the right-hand side to actually simplify the tree?
Yeah.
It's interesting.
Using a lot more memory to represent the same thing.
Yes, I agree. For that one, it's not exactly quite mentioned in the scope of the textbook. I can look into it and let you know. So Ashkan's question was a valid concern. His concern was like this. You can see the source tree, of course, is not no good. It's going to result in infinite loop. But the right tree doesn't seem to be good either because it got epsilon. Actually, we do have something there. We'll see that. Today, we also talk about how you can remove epsilon production. So that might solve the problem, which means once you got this particular grammar over here, is it possible to transform it into another grammar, let's say, and then you got to remove all the epsilon production. That might help. Okay, I think that's your concern. Good point. We're going to see that.
Yeah, well, here it would actually help because like literally the extra nodes are the ones, the two associated to the epsilon. The epsilons are compared.
Yeah. Anyway, we'll see that. Okay, good. Okay, so this slide mainly just to get some intuition, and then we're going to see the algorithm. Okay. Before we see the algorithm for removing left recursion, can we try to trace this particular string? Basically, I may not trace the whole thing. I want to trace just enough for you to get an idea. Okay, tracing that's quite tedious and error prone. We're not supposed to trace it in its entirety, but I'll just do a little bit for you. Okay, basically, here's the thing. Eventually, we're going to hope the algorithm we run for the top-down parsing is going to parse this exactly the same string. We are going to be able to build an abstract syntax tree looks just like this. That's our hope, right? But now I might just trace to build part of the tree, maybe show you a little bit of how backtracking works so you get an idea, okay? It might be a nice exercise for you when you have enough time, okay? Now in the class, we'll just do just enough. Okay, let's take a look. So let's now go on to this particular trace. Okay, so now this is the grammar that is not going to give us any infinite loop. So infinite loop is not in our way. And then the same string. Okay, let's try it quickly. Okay, this is your algorithm. Okay, I may just refer to some line over there, but I'll rely on you to be a little bit more familiar with it. I'll start with basically, so here. First of all, we're going to create a root for the start symbol, which is expression. And then I'm going to refer to E, E prime, T, T prime, and F. Okay, I'm just going to be a little bit briefer for the notation. So first of all, we're going to create a node for E. And then we're going to make it a root. Eventually, if the AST can be built, we're going to return this particular root. So we have the whole tree. And then the focus over here, let me just put a focus here. The focus tells us which one should we handle. The focus is going to be E. So notice the color. So I will put different color to show you. And then we're going to have an empty stack called trace. Okay. Okay. So now let's call that. Oh, sorry. So now that one is trace. And initially, it's just going to have null. Okay. For your particular implementation, you don't really have to put in null. You can just modify it so that maybe empty stack means you have success. Okay. And then the word is going to be the next word. You can think about this it's going to be a sequence of tokens we're going to read in for the algorithm. So the first word is going to be just A as the first word. Okay, so the word, I'm going to put it over here, is just going to be A. Okay, that's how we set it up. Okay, and then if you look at the state condition for the while loop, it's over here as true, which means potentially we might have to run an infinite loop, but we are not going to. It's guaranteed to terminate somehow. Okay. So now let's look at that. So we check the condition here. We check to see whether the focus now is E. Is E one of the variables? It is. You can see the E here is definitely one of the variables, which means we can potentially choose some production rule. Okay? And then the next step is we're going to go into this particular branch, and now here is the most important line you have to see. And then I'll highlight something that we'll see later. Okay, look at the line I just highlighted. Okay? So here it says that if there exists certain unvisited rule for the focus, right? Focus is now E, right? In this case, there's only one rule we can choose, so we have no choice. But in theory, you may have more than one choices over here. For example, let's say E prime. You got two choices. When we as a human to choose, we can be very smart. You might choose to get epsilon as opposed to the first rule. But for running the algorithm, you have to go with a particular order. For example, in the order in which the production rule appears in the grammar. So that's why backtracking might be necessary. Okay, just want to give you some insight. You can. Yeah, let me just remind you quickly. Okay, I would suggest for your best bet, you may want to review how depth first search algorithm works from your 3101. Because the way things work is very similar when you go backtrack using a stack. That's some analogy I'd like to draw. Okay. Okay, let's go a little bit further. Okay, I don't want to spend the entire class on this. That may be a little bit too boring. Okay, let's do a little bit more. Okay, just get enough for you. Okay, the orange part, basically we're going to choose something here. Let me just say, I have no choice, so I'm going to choose this particular one. I'm going to choose just this, the blue one. Okay, let me make it a bit thinner. Okay, so now that means I'm going to build as follows. So now for the blue one, I'm going to say T and also E prime. And did you notice that we are basically on our way to build this tree, right? Automatically, right? That's the beauty about this algorithm. And then, once we have done that, we have to make sure do this routine over here. Let's go review a little bit. We did it last time. The children is going to be T and E prime. And then we're going to put everything into the stack except for the first child, because the first child will not be the focus. They don't have to be in the stack. So we have to push E prime into the stack. And now the focus will now be, you will see beta 1, the first child. So now the focus will be T. Okay, I'll pause a little bit. That's the first iteration. So this scenario means we can expand the tree further down one level. If the current focus is actually one variable for which you have some unexplored rule, you can expand the tree. Okay. Later on, you can think to yourself some scenario. If somehow the focus is E, let's say, okay, we are now in the start symbol. However, when we check to see this particular condition, there is no unvisited rule. So what does that mean? Anybody? Let me make my question again. Okay, here's a question. Let's say the current focus is E, the start symbol. And then when we go into this if condition, of course, E is a variable. And then when we check this particular if conditional here, let's say we have exhausted all the rule, but so far there's no lock. Chelsea.
Does that mean you start by being given a string? So if you exhaust all the rules you're looking at, does that mean that you cannot share it because you have to?
Not quite. Not quite. Coco.
Are we at the top of the stack first? If we're at the top of it, because we look down all the way down.
Yeah, so basically if the current focus is actually the start symbol and also you have exhausted all the rules, that means you basically backtrack all the way back to the very first step. There's no possible step you can ever make to derivation to make this particular input stream work. So that means syntax error. Right? That's one way of having syntax error. Okay, so that's why you will see this particular branch over here. Okay, okay. We don't really see this branch for this simple example because it's valid string. Okay, okay. Let's go further. So now we are done with the first iteration. So now we'll go back to the beginning of the while loop. Okay. So now let's have a look at here. The focus is now T, right? The term. And then we check to see this particular condition here. Is T a variable? It is, right? T is a variable. And then we're simply just going to run this particular, we're going to check this particular condition here. So now for T, you can see this is the only rule we have. We have not seen that yet, right? So that means we can now explore it. We'll go for that particular branch, okay? So now what I would do is, I need to change the color so you can see more. So now for T, let me say green, okay? I'm going to use this rule. So that means for this particular T, I'm going to have factor and then term prime. If you look at that, right? That's what we have done, right? Let's go to a little bit more. And then for this guy over here, the same, okay? It has two children, only the non-first child is going to be pushed onto the stack in the reverse order. And then now the focus will be factor. Okay? So far we haven't seen any backtrack just yet, but we might see that very soon. Okay? Guys, any question? We okay? All right. Okay. So far, hopefully nobody is lost.
How do you build that tuning unvisited?
Good question. So somehow you can see the way I did it is very informal. I just try to just aim for understanding conceptually. So when you implement it, you may want to say maybe you have to annotate your grammar objects such that maybe every production rule object has a some like a color or some Boolean flag. But you got to be very careful because you're going to see a little bit later. Because for a single production rule, you may have to apply that multiple times at different levels. When you say I'm visited, it's only I'm visited for that particular level. So you got to be. So that's something I left to you as an implementation. That's a challenge. Okay. Yeah. Do you have to implement that for assignment 2? I tell you a very practical concern. If I could do it within the next couple of days, then I might make it assignment 2. If I found it too overly too complicated, then I would say, okay, you guys, that's too harsh. Is it fair? Okay. Well, you know, actually many of you guys are better programmers than I am, so I wouldn't worry too much. But you know, I want something reasonable to you, right? I think, but of course, programming this would be very interesting programming exercise. Very interesting, right? It's more like you're thinking about a complex algorithm in 3101, not the most difficult one, but you try to put it into code and make it work. Okay, so now let's go a little bit further. So now we have a factor over here. So now we go back to the third iteration for the while loop, right? So now f. So now focus is now f. Is f a variable? It is. Okay, so now we're going to go for factor over here. So now we're going to see, for factor, do we have any unvisited rule? We do. There are 2, exactly. Both of them are unvisited. Let's mark them. So now I'm going to mark them possibly using orange. Let me just go by their order. But now you might see that we are going the wrong way, you see? Okay, that's good. Let's see. Exactly. I'll just show you a little bit about backtrack, and then I'll leave the rest to you. Okay. I think that'll be enough for your understanding. So now for f, over here is going to be parenthesis and expression, and then parenthesis. Okay, that's pretty good. So now we have to push the, well, again, push the children, which will be closing parenthesis and also expression. So now the focus will be the left opening parenthesis. Okay with that? Okay, so now if you go back to the beginning of the while loop, first of all, currently the focus is opening parenthesis. Is it a variable? No, that's the first time we're going to see some different branch. So we're going to go for else if. Okay, so now does the word, which is A, match the focus? The word is A. The focus is this. Does it match? Doesn't match, so we don't go into this branch. And then we go into this. Are we now at the end of the file? No, apparently not. We're only here. Right? That means only go to else and backtrack. Okay? I think it's most important for you to understand why we need to backtrack at this point. Because whatever you have derived so far just cannot match. So that means somewhere along the ancestor path, your initial choice is wrong. Okay. So now let me just go a little bit further for you. Basically, you will see in your slides, I define the backtrack as follows. Backtrack simply means you have to somehow pop all the children for the current focus. I'm going to show you that. And then you have to switch the, basically you want to switch the focus to its parents. And then you have to reset the children. Okay, let's see how that can be done. First of all, I'm going to do the following. If I try to pop all the children, so get rid of this, okay? And then the focus now is going to be the parents of opening parentheses, right? So now that means the focus now is going to be back to F. And now I'm going to reset the tree. Right? I'll just, well, conceptually, you can think about just wipe it out. Make it smaller. So that means we have to maybe try another way. Right? For factor, maybe we should try with A instead. So now when we go back to the iteration, when we check to see unvisited rule, so now we can try A. In this case, A will actually match over here, right? Just go on and on and on. Coco. Yes, basically, can you tell me which input you might be thinking about? That might be easier for discussion.
The step, for example, let's say you have a rule that.
You're talking about an ambiguous grammar.
No, let's say you can't parse it. So let's say you have.
Okay, just give me one example. You mean this example can be parsed for sure. That's not a good. Yeah.
But let's say you have in your grammar you have v times variable equal variable gives you variable multiplication of the variable. But then the left side we had one example. I can't really recall it.
You know what? Let me consult with you about the example you're thinking about. Let me present it maybe next time. That might be easier for everybody. Yeah, approach me after class. Okay, Chelsea.
I don't think this is a stupid question, but how does an epsilon work? Because like we could use it.
Oh, the epsilon. Yes, epsilon. Good question. So what Chelsea's question here is, what's going to happen if, for some reason, let's say, somehow in the middle of halfway through the execution, let's say we already explored this particular rule. Let's say that's how we backtrack. And now when we backtrack to term prime, and now we need to do epsilon. Okay? Conceptually, epsilon is pretty much like you don't need to do any work. You can just, it's as if you want to backtrack right away. It's actually mentioned in the slides. Yeah. Okay. So guys, what should you learn from this particular slide? My expectation would be you will actually try at least to try to trace this particular simple input in its entirety yourself. Okay? It's going to take a long time, I know, but I give you just enough information in the class so you can try to do it. If you got trouble, come to me. Miska first.
If I recall right, epsilon means acceptance state.
No, epsilon is like epsilon production, right? In the context of CFG, let's say if you say, for example, here, let's say term prime generates epsilon, which means this particular variable can just reduce to epsilon like an empty string, right? If you think about it, thinking this way, what we said before, if you look at all the leaves for this particular pink AST, it's going to be A epsilon and also A times A epsilon. If you combine them together, right? A epsilon plus A multiply A epsilon. Epsilon is like an empty string, so it would just be equivalent to A plus A multiply A, right? Yeah. But who?
Basically, Yann tries all possible.
Exactly.
So it's a brute force.
In some ways, brute force. It's a good observation. Well, what you think about is it's brute force. It's trying to exhaustively try all the possibilities.
Yeah, because when we use background,
Yes.
we don't have a kind of heuristic way of exactly.
So now let me go a little bit look ahead for later. Okay. So now apparently the performance bottleneck for this algorithm is if you're really bad in luck, somehow you organize your grammar in a way that always the right rule is the last one, for example, right? In that case, well, too bad. You will definitely you got to try all the possibilities before you can reach derivation. How can we make our parser slightly smarter so that we can prevent backtracking? That's the question, right?
Now, can we
Say it again.
Less number of rules for
No, actually, the number of rules is fine. Somehow, for example, let me just say something quickly. It would be very nice to maybe somehow modify our algorithm, especially this particular step. I'm talking about this, right? Specifically this one. To say, for example, when I'm reaching factor, I want to be smarter in this case. Rather than choosing this one, just happen to be the first one. I don't want to choose it. I want to choose maybe A. No, no rewriting the grammar. Grammar is the same.
Randomized algorithm.
I'm not even sure how that works.
You randomly pick one of the ones that we want to visit.
What? But to be honest, I gotta confess, I know nothing about randomized algorithm myself. But since it's random, right? You still got the possibility of.
But the idea of typically randomized algorithms is that if it's unlikely, then you're basically moving the adversary out of the way. That it's very hard for there's no way the adversary can give you a bad answer. It's only bad if you make bad random choices, which typically
Yep.
you can make something of probability.
Am I right? It's somehow based on some probability.
Yeah.
Okay, but there's a simple modification which doesn't even require randomness. Yeah.
Well, can you just, instead of choosing the first one, choose the last one, since the last one
Well, in theory, you may have a number of rules. Maybe the best one is the middle.
How about we
but that one may not actually be the one you want. How about this? Is it possible to make a simple modification? Okay, it's unfair to you guys, but just think about it, right? Since you don't know this, I know the solution, so that's why I can make it sound confident, right? So here, I want to make slight modification to this line here, so that when I pick the rule, I'm guaranteed to always pick the optimal. No randomization. Okay, it might work. You can let me know if you got something to work, but we don't need it. Chelsea, if you got questions.
No, you're on a different track than I was. Just keep going.
That's fine. Okay. Okay. Okay, we'll definitely get there towards the end of today. The idea would be we're going to introduce something called look ahead. Easy in the following sense. Let's say, remember I was over here talk about factor, right? So now, in order for me to decide whether to choose this guy here or this guy over here, basically I need to have a way to look ahead the input. I will know that what I'm expecting is in A, somehow, so that I will choose this one. So that can avoid me actually going for this branch and then backtrack later. That's just conceptually. But exactly how to calculate the look ahead systematically, that will be the subject a little bit later today. Okay? Look ahead, basically. Okay, any question about this? Any general question? Okay, what can appear? I wouldn't say this might appear on the quiz, right? That might be too complicated. Maybe in the exam, I'm thinking out of my feet, right? On my feet. I might simply say, for example, what I said before, let's say currently the focus is actually the start variable. And then we have no unvisited rule. So what does that mean? You want to describe in English what that means. So I really want you to have some understanding about this particular algorithm. But I'll definitely give that to you. Question? Oh yeah, don't memorize, please. Don't memorize. Don't waste your intelligence memorizing it, please. If I do ask you a question about any algorithm we talk about in the class, I'll definitely give the code to you. That's not a problem, okay? Question somewhere? Okay. Again, try to trace the code and then approach me if you got question. Okay, I got some exercise for you. Andres actually mentioned something on Wednesday. Okay, you will worry about, let's say this. Should this be considered as a possibility of infinite loop? The answer is no, because this is not really a left recursion, neither direct nor indirect. Okay, you can see basically factor simply just go to the first symbol, the leftmost symbol is basically left opening parenthesis. So that one already break the recursion. Okay, what's going to happen? Okay, this one will be an exercise for you. Okay, so now I want you to think about how you will trace this particular one. Okay, so two exercises. Try to complete this one if you can, and also try this one as well. It'll be similar, but try to see how the algorithm works. Okay, any question for me before I move on with other things? Derivation, leftmost, yeah. Oh, okay, let me get it clear. Let me summarize, yeah. Okay, let me just clarify some terminology here. We basically, so far we talked about something called top-down parsing. Okay. Later we'll talk about bottom-up, maybe next week. Okay. Maybe expand, maybe a little bit over, maybe the reading week, possibly. Top-down parsing, and the way to think about what it is doing is it's trying to automate the process of leftmost derivation. Remember, before we talk about this particular algorithm, when you do leftmost derivation, you always rely on your intelligence, right? Always do it manually. Okay, but now in order to do this, in order to make this automatically work for the algorithm, okay, there's some precondition there. Okay, precondition. The precondition is the CFG, the grammar you're talking about, can not contain any left recursion. And I will talk about the kinds of left recursion in just a moment. Okay, left recursion. So here, either direct or indirect. Okay, that's a quick summary of what we have seen so far. Okay, just get the big picture right. And we're going to see a little bit more of course, to satisfy this particular precondition, so that means we always get some context-free grammar that is right recursive. So that's going to work without triggering any infinite loop. And there's something I just mentioned a few moments ago to say, in order to really get some efficient performance, okay, in order to do this, we want to do some look-ahead process to avoid backtracking. So this is kind of the mental roadmap you want to have when you study top-down parsing. Yeah, but we'll talk about each one of them.
So right recursion will never lead to.
Correct. Right recursion is guaranteed not to lead to any infinite loop, but right recursion might lead you to backtracking, which might also compromise your performance at the runtime. Oh, we'll talk about direct versus indirect in just a moment. Yeah, we'll talk about it. Okay, since everybody is okay, reasonably. So now what I will do is, let's talk about the kinds of left recursion quickly. Okay, two exercises for you. And now the question what Chelsea was asking, what if you have some, let's say, epsilon-production when you do the tracing? Okay, I tell you what, there are two options here. Either you can get rid of all the epsilon-productions. In that case, we'll learn about the process. We'll do this very easy to do. Okay, or the way to trace it is as if you're done with the current focus and then just gotta backtrack. Okay, I'll just mention that here. Okay, when you do the tracing, you can apply that. We will terminate because right recursive, guaranteed. So now, let's now learn about, before we learn about the systematic approach, let's just see the recursions. Left recursions, specifically. Direct versus indirect. So now, let's define this. We say that a grammar contains a cycle. Okay? If I beg your pardon, I should read, it's a very serious typo. There should not be a star over here. Oh, actually, you know what? That is okay. Sorry. Yeah, that's fine. Sorry about that. Yeah, there was no typo. What I meant to say was, your grammar may contain a cycle in the following sense. Okay? Yeah, you maybe start with E, for example. Let's say start with A, make it very general. Start with A, maybe somehow A will go to maybe B, and then B might go to C, and C will go to A. Right? In that case, you know that from A, I can eventually go to itself. That's a cycle. Okay? Just make sure you understand that. Okay.
What about having starting from 0
Say it again.
Start from 0 2.
0 means maybe I should make it plus, actually. Yeah, I agree with you. Okay. So I think this one means either, well, if A derives A directly, well, it's adding a single derivation. So I should put a plus here. That means at least one.
Actually, in the slide, it's not the regular expression star and plus. It's just star represents an arbitrary number of like steps in the derivation. It's one dimension.
Let me double check. Yes. Let me double check with this definition here, and then I'll see if I need to fix it. But the idea would be such thing, for example, is like a cycle. Okay, good. Yes. Okay, what about direct left recursion? That means you have a production rule like this. You have some variable A produces itself followed by something. So it's a leftmost variable on the right-hand side. That's direct. Okay. For example, first example here. So now you can see, I may just switch to iPad quickly. Okay, so you can see that. Why? There should be left recursion here. Give me one moment. It's here. Okay, let's just go over that quickly. Okay, basically for left recursion, you can see, for example, expression maps to expression. That's a leftmost symbol, right? That's one occurrence. And turn, also you can see the leftmost is also turn, right? So you got two occurrences of direct left recursion. Similarly, on the right-hand side, expression, also you got expression here, and turn, you got turn here and turn here, right? You got four occurrences, left recursion. What about indirect? Indirect means what? Just indirect, right? So it's not direct. Now, do you see some indirect cycle here? Well, not really cycle, I gotta be careful. In any indirect recursion. Okay? You can see somehow A will lead you to somehow B, and B will also lead you to maybe C, and C will also lead you back to A. So that's indirect. And all the variables that we're talking about is basically on the leftmost. Okay? Specifically. So whenever I ask you about, let's say given this particular grammar, I want you to tell me, is there a left recursion? Let's say indirect. You can tell me there's indirect left recursion because of the following two conditions, right? First of all, you want to say A produces BR. Okay, you can see B is not the same variable as A, first of all. That's the first one to show. Okay? And number two, you somehow want to show me the following. You want to show me that for B over here, if I try to do a number of derivations, I can eventually get into something start with A. Okay, what should be that something here from what you can see? TDR? The reverse, right? Yeah, let me just make sure, yeah. No worries. TD, basic, just TD, yeah. Okay, let me take a look, okay? Yeah, okay. Oh, yeah, exactly, yeah. So R is already here, so you don't need to mention that, okay? Good, okay. So guys, let me just make it clear again. So now, the first condition you got to show is A produces something that starts with a different variable. That's the first thing, okay? And then you want to show that by a number of derivations, you can go from that particular variable, which is not A, eventually get to a string that starts with A. Okay? In this case, it will be TD. Okay? As for why it is TD, I'll leave that to you. It's TD. Is it clear for this one? Okay, why don't you try for a second example? Okay, so number 2 over here, right? So now, let's say I'm giving you this in the quiz number 3, not quiz number 2, don't worry, right? Quiz number 3. Now, is this particular grammar left recursive? So now, it's indirectly left recursive. So now, how do you show it to me, right? So, okay, I'll start you with, okay, first of all, it's A produces B, A, okay, you can see B is not A, right? And now, somehow B, by a number of derivations, can get to something that starts with A. And what should that be? Huh? A, F, D, and you don't need to include A. Yeah. A, F, D? Okay, let's check. Okay. Yes, pretty good. All right. Okay, I'm going to pause a little bit to see if everybody is comfortable. Okay, showing direct left recursion versus indirect is a little bit different, right? So now I think that for the indirect left recursion, you just got to see the cycle. Sorry, I shouldn't say cycle. Cycle has special meaning. You just want to see where the derivation comes from. Okay. Any questions about this? Okay, so that's about the kinds of left recursion. So now let's say given any one of the 4, for example, you want to somehow have a way to systematically convert them into right recursive grammar so that it can be the input for top-down parsing, right? So now the algorithm which we're going to see is very symbolic. I'll try to explain to you at a high level, and then we'll run some example. Okay? Basically, the algorithm is going to contain 2 stages. Stage number 1, try to remove all the indirect left recursion. And stage number 2, try to remove all the direct. Indirect first and then direct. Remove them one by one. Okay? That's going to be what the algorithm will do. But we're going to see. Okay, so now the algorithm looks like this. Very symbolic. Okay? Don't worry, I'm going to help you a little bit to read it. Okay, I'm not going to go too many details because I do have examples for you. Okay? Bear with me. I'll try not to spend too much time on this, right? Okay. Let's read it quickly. Okay. Also, you can see the slides later. So now the algorithm is to remove the left recursion, both indirect and direct. Okay. So now the input will be some context-free grammar. Itself may or may not contain the left recursion, may or may not. We assume the following. First of all, there's no cycle in the grammar. Okay, we'll just talk about the definition for cycles already. There's no cycle, and also there is no epsilon-Productions in the grammar. No, it's different. When we talk, that's why I want to be a little bit more careful here. So when you study, make sure you read about this particular definition for cycle. The cycle has a very special meaning. You go from A to just A itself. So left recursion is not considered as a cycle. Okay, please make sure to read that definition clearly. Okay, that's why I put it at first. Okay. Okay, and then okay, algorithm. Let's go back here. So these are the two preconditions: no cycle, and also no epsilon-Production. Okay, we'll talk about how to remove epsilon-Production a little bit later. Okay, the output is simply just going to be another CFG. Okay, such that they are basically equivalent. Remember, I talked about briefly about semantics preserving. That's something you can assume the algorithm is correct. And also, the output grammar has no indirect nor direct left recursions. Okay, that's kind of the input and output. Okay, and the procedure is actually, you can see the algorithm is not very long, right? It looks complicated, but it's okay, right? Let's do quickly. I'll try to, okay, the first line here is very important. Impose an order on the variable. Remember, for context-free grammar, the variable is a set. But now we want to go over the set in a particular sequential order. But I'm going to show you. In a way, we're going to, for example, let's say for this particular grammar here, I'm going to name this arbitrarily. Let's say 1, 2, and 3. That's one way to impose an order. Okay, that's what it means for the first line. Okay, and then we're just going to go over from maybe from 1 until n variables, right? In this case, I'll go from 1 until 3. Okay, good. Now, there are two stages. Stage number 1 and stage number 2. Okay? The first stage is going to remove indirect left recursions. The second stage is going to remove direct left recursions. Okay, so that's good. Okay, it's two stages. Okay, just you can keep in mind. And now I'm just going to mention a little bit more details about the algorithm itself. So when you study that, you can pay attention to the detail. Notice that the way we write a loop is with a pattern. It's a nested loop. We got I and we got j. I is from 1 to n, and j is from 1 until I minus 1. So it should be quite a familiar nested loop pattern for you, right? For example, when you were trying to check if there's any duplicates in an array. It's more like an index pattern you are familiar with. Okay, we're going to see that. And then for every iteration for the inner loop, you're basically going to check for this particular condition. Okay? This particular condition over here. Okay? It looks complicated. Let me try to help you a little bit. Okay? Let's say this. Let's see. Make it bigger. So now, if you have a production that goes from AI into AJ something, and notice that I is guaranteed to be larger than J, because J only go from 1 until I minus 1, right? For example, let's say if currently I is actually 3, for example, let's say if J is equal to, let's say 1. In that case, you can see C is basically produces A. C has an index 3, A has an index 1. So that means now C is now produces a different variable. So that means we have a possibility of entering some indirect left recursion. So if you see the textbook, the way to describe this algorithm is called preventive, which means we don't necessarily find the left recursion and then remove it. We just prevent that from happening. Okay? Anytime you basically have any variable with a larger index, if that produces just another variable with a smaller index, you try to rewrite it, basically. Okay, something to note. Okay, but we're going to see exactly how this works. Okay, so now if you have that, and then let's say for this particular variable here, that one produces, let's say, delta 1, delta 2, all the way to delta n, right? So that means you're going to replace it by a, let's say this, ai produces aj gamma, right? And then also we know that for this particular aj, it also can produce this delta 1 or delta 2 all the way to delta n. So now we can rewrite it in a way. ai should produce delta 1 followed by gamma, or delta 2 followed by gamma, or all the way to delta n followed by gamma. That's kind of the step. It's a bit tedious to show it here, but just want to get, once you understand the example, you may want to review the algorithm to see how that works. Okay, that's one way. Okay, that's basically the basic step for removing preventively the indirect left recursion. Okay, so now for this guy over here, okay, this one here, I will explain it using an example. For that one, I will let you read it. Okay. Any question, if you have any, at this level? We're going to see some example for sure. Okay, let's see some example. I got 4 here. Let's see how many we need. We might just need a couple. Okay. What I will do is let me wipe it out over here to make it clean. Okay. Okay, let's trace it quickly. Okay, maybe for the first one, we're going to do a little bit more detail. Basically, for this one here, that's the input grammar over here. Okay. Apparently, you can see there's no direct left recursion. Agree? Okay. No direct, but doesn't matter. Let's run the algorithm. When you run the first line, impose an order on the variable. Let's call that A1, B2, C, and 3. So when you implement this, you may have to augment your grammar objects with attributes. Maybe call that order or index, something like that. We have a global hash map, whatever you like. Okay, and then so now when we do I is going to be 1. Okay, so thinking this way, I and j. When I is equal to 1, is the inner loop going to be run at all? Not really, right? It just only go from 1 until 1 minus 1, which is 0, right? So now this is not applicable. When I is equal to 2, so that means you only consider j is equal to 1. Agree? When I is equal to 3, you're going to consider 1 and 2. That's basically loop counter pattern. Okay, I assume everybody's okay. So now we know that this guy here, basically nothing for the inner loop to do. So we can just bypass that. Okay? And now what about the next one? When I is equal to 2, we only consider 1. So now you can see over here, I is equal to 2. And then we're going to consider 1. Let me be careful here. Okay? So basically you're saying this. We are checking this particular if conditional. Okay? So now apparently you can see we have B here. You know what? Let me give you a little bit exercise here before I tell you the answer. Now I see the trick. Now I want you to look at, that's really the trick when you trace the algorithm. Look at this particular condition here. My hint to you, pay attention to I and J, okay? And now, do you think this particular Boolean condition will be true or false? At the moment, we have, at the moment, I is equal to 2, and J is equal to 1. Okay? Oh, so but if you, okay, first of all, should that be true or false, first of all? That should be false, but now we want to look at that another way, okay? B over here goes to C, right? should it be considered as a possibility of indirect left recursion? Not according to the algorithm. Because over here we say that it should be such that I and j, where j should be strictly less than I. But now you can see b is 2, and c is basically 3. It's bigger. So which means at this point we don't really handle that. Okay, there's a subtlety here. Okay? Good.
I think you see the step for second form.
Which one?
For AI goes to AI up.
No, actually, let me, okay. Yeah, let me go a little bit further. Okay, so hopefully that will help a little bit. Basically, when you actually go for the third iteration for the outer loop, so I will now be 3. So now we got to check for 1 and 2, right? So now, when I is equal to 3, so that means we're basically looking at variable c. Okay, c produces basically a over here. Agree? Okay, so now c has an index 3, a has an index 1. So that means we have to do a little bit of transformation over here, according to it. So what we will do is, given this, c produces at. Okay, that's something we're given. Okay, that has an index 3, that has an index 1. So now we have to transform it to, so now a itself produces br. Agree? So now that means we should do the following. So we should say, replace it with, this is basically the line I'm going to execute. Okay? C produces, and then I'm going to say br, and then t. Okay? This is basically the third iteration of the outer loop, but the very first iteration for the inner loop. Okay? Should we go a little bit further? Okay? When you go a little bit further, you're going to see, we're just going to refer to this. So now b over here, again, index 2, and c is index 3. Also, this is strictly smaller, so we can also try to replace it again. Okay? So now, for that, c will produce b here, cd, thank you. So now that'll be c, d, r, t, right? But what do you see here? Somehow, there was no direct left recursion in the input grammar. But after after trying to preventively remove all the indirect left recursion, now we have direct left recursion. That's why we also got a second stage to go further. Okay. Okay. So now, how do we remove? So after this first stage over here, this is basically what we will get. For example, one of them. Okay. How do we remove the the direct left recursion? Okay. When we execute this particular guy here, okay. So now what we will do is look at this. Okay. So now we will say C produces C D R T. Okay. That's the only rule we have. Okay. Basically, the algorithm tells us if you have the shape of the direct left recursion, so you got the same variable, exactly like that. What you will do is, you can think about the alpha over here is like the DRT over here, okay, like that. And then the alternative beta, there's no such thing, just epsilon. You can think of it, yeah, like epsilon here. Okay, and then you want to replace it with basically C produces. And now beta will just be epsilon, just nothing there. I'll say C prime. And then C prime over here will produce basically the alpha and then C prime. Alpha is DRT. So this guy here is, I'll do more example with you. Actually, in here, the epsilon is not part of. For C prime, you mean to have epsilon here? Actually, in this case, we don't need to, because the only rule that we're considering is simply C produces C DRT. Oh, yeah. That's good. Yeah, you're right, yeah. Yeah, there's an epsilon here. Yeah, you put it. Yeah, basically, that one is saying, I'll try to do another one with you. And here, this one, I just try to trace a little bit more closely. when you try to do the prime here, you want to do alpha concatenated with that also in epsilon. We'll see a little bit more clearly why it's necessary. Okay. Okay, this grammar is intentionally easy, but tracing it is a bit tricky. Okay. Any high-level question for me before we just do one more example? Okay. Yes.
So, in the last work, like, what if you have multiple alternatives?
Oh, good question. Very good question. Abdul's question was like this. When you say, okay, basically, here we say AI, so there's a direct left recursion. Here you're saying, what if beta has many multiples? In that case, you got to replace for every one of them. We'll see example like that. We'll see, yes. You got to replace every one of them. That's why, implicitly, when I say this particular for loop, I'm saying for every such shape, in that case, you can think about the, I'll give you one example. And I'll go to your question. If I got E produces E, let's say plus term, okay? Or F or G, for example, right? In that case, the way I remove it, you can think about this is one possibility for beta. This is just another possibility for beta, right? Okay. So now the way I convert this into a right recursive is by saying E produces, according to the rule, okay, so here I'm going to say the beta, right? The beta can either be F or it could be G, right? Followed by the new variable, which is E prime. Okay, so now E prime over here will be the, it will actually be the alpha, will be the alpha part over here. So alpha will be whatever that follows the E, which is plus T. So that's why the grammar looks a bit funny here. That would say plus T followed by E prime or epsilon. Coco. Then you got to handle one by one. You can, yeah, yes, you can either handle one by one. Okay, good question. A similar question was like this. Let's say if I introduce, let's say, or over here, let's say E multiply T, for example, right? You got two options over here, okay? You either simply just handle them one by one. Okay, maybe you try to, what I meant was this. Let me try to make it clear. I can try to handle, first of all, this together with these two, and then I create something called E prime, okay? Or I can try this, I can try this together with these two, and then I make it maybe E prime prime. That's one way to go. Or if you're being clever enough, you can also try to collapse these two into a single variable. That might also work. Of course, if you want to make an algorithm out of this, possibly having separate variables is easier for you to code up, right? Depends the context. Okay, seems a little bit overwhelming today, right? We're so fine. A little bit. Okay. I think once we finish chapter 3 about the parsing, I think we finished hopefully the difficult part for this course. Later will be a little bit more application. Okay, but we'll try to go a little bit more slowly at the beginning. Okay, we've got about 15 minutes. I would suggest the following. I will continue with maybe a little bit more examples over here. I would suggest before Wednesday, can you try to review the top-down parsing algorithm and try to review this particular one to see how you can remove left recursion. After a little bit more study, a little bit more struggling, I will try to do either one or two more examples together so that can strengthen your understanding more on Wednesday. Let me just move on to the next topic. Okay, I'll definitely revisit this. And try to see how you can remove left recursion for this one. This will be fun. Okay, try that. And also another two. Okay, let's do something easier. Okay, I hope. Okay, that's about the algorithm. Oh, that was interesting. You guys learned about looping variant, right? 3101? Yeah. And maybe a little bit in 3311, right? Yeah. I would say, basically, this particular loop over here. We got nested loop. Here's my question for you. Okay. Basically, imagine that between line 8 and line 9, I want to insert a looping variant over here to say at the start of each iteration for the outer loop, there's certain condition that will actually hold. Okay? I wouldn't push you for answer on this, but I would suggest think a little bit about this. Hopefully on Wednesday, once you go through this algorithm for a few examples, we can talk about looping variant. For now, it may not make too much sense. Okay? So what I will do is I'm going to go very quickly so you didn't see it, right? Okay. Think about the looping variant. Okay? Think about it. All right. Okay, so now let's talk about another topic. How to eliminate epsilon-Productions. So this one I didn't really have an explicit algorithm written down for you because that one is rather easy. Again, it's more about thinking about possibilities, but let's just talk about quickly. That one's easy, we can do. Okay, motivations. The top-down parsing algorithm requires there'll be no epsilon production, right? Typically, okay? And also, once you actually produce this context-free grammar, what I meant to say was, sorry, this line doesn't make sense. I should really rewrite it, sorry. What I meant was, when you actually run the algorithm for removing left recursion, it might generate a grammar that contains epsilon production. But now, you may actually want to remove it sometimes to actually reduce the size of the tree, right, as you mentioned. Okay, I'll rewrite this line, sorry. That's a little bit of typo here. Let's talk about it. Every time, if you want to remove epsilon production from your grammar, there's one thing you want to make sure for the approach we're going to show you. If it is for sure that epsilon, like an empty string, is not an accepted string for your particular language, then you can feel free to use this particular approach. Because once we remove all the epsilon production, of course, empty string cannot be produced. Right? It's always a non-empty string that can be derived. Okay? But I would say that's a safe assumption to make, usually, because you don't just want an empty file to be accepted, right? Usually. Okay, so now we want to say that if you're pretty sure epsilon is not supposed to be accepted by your language, you can definitely use this approach. Let's see how we can do that. Okay, okay, epsilon production simply means if you got anything, a variable that produces epsilon, that's an epsilon production. Okay, that one's just get it clear. How can we remove it? So now let's make some definition. Oh, did you guys learn about this back in 2001? No? That's okay. We'll learn it now. Okay. By the way, did you learn about Chomsky normal form? Yeah. Okay. Then I'm a little bit surprised. I thought in order to make something Chomsky normal form, you have to remove all the epsilon productions.
We probably talked about it, but I think it's 3 years ago or 2 years ago.
That's true. That's true. I wouldn't blame you for that.
The name is catchy. Yeah.
Chomsky normal form, right? Okay, yeah. Yeah. Did you guys go further to say, once I got a grammar in Chomsky normal form, I will try to prove the pumping lemma for context-free language? Possibly, right? Anyway, don't worry, we're not doing that.
Yeah, we have.
Yeah, I guess it depends on the professor, yeah. Actually, it's fun. It's fun. Okay, let's focus on this. So now let's define the following. We say that a variable is nullable if by a number of derivations you can go to epsilon. Okay, easy definition. Okay, so now each terminal symbol, of course, is not nullable, right? Because that's guaranteed to derive something that's not empty string. And now variable A is nullable. You want to think about what might be the definition for that. How can I say my variable is actually nullable? Okay, I'll go a little bit on your thought. Okay, try to see, maybe we can improve that just a little bit. Yep, of course, we're going to go recursively. That's not an issue. For example. So now, first of all, we know terminals, for example, A, is not nullable. Okay, that's something we know pretty well. Let's say, what about variable? If I got A produces epsilon, of course, it's nullable. A simple case that you were talking about, for example, if I say B produces C, C produces D, and D produces epsilon. That's also another case. So we can say B and also C and D. nullable. Okay, we're seeing different cases. However, this case is not general. In general, you may not just have this is called unit production, right? You don't just have a single variable after the produce is signed. A general form would be something like this. Yeah. So okay, you're getting there. So let's try this. If I say B produces something like this, let's say alpha 1, alpha 2, all the way to alpha n. Each alpha may be a variable. It might be a terminal. Why should better be variable, right? So now, what does it really mean when I say B is nullable? If
alpha 1 alpha n,
should it be just one of them or all of them?
one of them. All of them.
Huh? Some of them was like a between for all and exists, right? No.
Because if only one of them is not nullable, then like, you can get rid of the rest of each other.
Yeah, exactly.
And now one
Exactly.
reduce your non-term.
Mhm.
Non-epsilon.
Yes, yes,
You need all of them.
yes. That's correct. So let's say in general, a variable produces a number of things over here, right? If I can tell you alpha 1 is nullable, alpha 2 is nullable, and all the way to alpha n is also nullable, that means B is also nullable. It got to be every one of them. For example, if somehow, let's say somewhere in the middle, it simply got a terminal A. So now I can immediately conclude B is not nullable. It's guaranteed to always contain just A. So it cannot be epsilon. Okay, so now it should be epsilon, alpha 1, alpha 2, alpha 3, all the way to alpha n are all nullable. Okay, but we can do an example, don't worry. Just want to get something intuitive for you. Okay, that's exactly what I said, okay? Let's go a little bit further. So now, let's go for one more step, and again, we're going to do one example. Let's say this. If I got a production here, B produces CAD. Let's say C is not nullable. It's always there, for example. Well, actually, it doesn't matter. Okay. Let's say let's make an assumption. Let's C is not nullable. D is not either. But now, let's say A is nullable. What you should notice is, because A is nullable, it's more like a binary choice, which A may be there or may not be there. Right? So that means I can either put A here, or I can get rid of A. So there are two versions. Okay? Everybody okay with this particular production here? To go from B produces CAD into B produces CAD or CD. Everybody okay with that? Okay, so now, here we only talk about just a single variable being nullable. What if there are n nullable variables in your production rule?
Wouldn't it be recursive?
Yeah, the way, of course, when you consider whether your variable is nullable, you got to do it recursively, of course. Let's say we have done that already. We already know which variables are nullable. So now let's say the following, okay? Let me do one more intuition, and then we got to do one example to make things clear. Let's say, for example, let's say I got A produces, okay? Let's say, I'll just say alpha 1, alpha 2, and alpha 3, okay? Let's say it's known to me. Alpha 1, alpha 2, and also alpha 3, they're all nullable. Let's say they are all nullable. In that case, well, of course, you can say alpha 1 may produce epsilon somewhere, right? But this is not relevant. We're just saying it's possible somewhere there. Okay? Let me put it aside. Now the question is, how can I rewrite A to somehow to actually take into account that alpha 1 may be gone because it might be epsilon, or alpha 2 might be gone? How many possibilities do I have? Is that 2 to the 3? Okay, exactly, right? Basically, alpha 1, either it's not there or it's there, right? Alpha 2, either it's not there or it's there. Right? It's not there, it's there. It's basically binary choices, right? Okay, so now we can rewrite it in this way. We can say that A, so now be careful here. let's say, let's be careful for the first one, and then you'll see why I need to talk about this. Let's say we use over here, let's say either all of them are here, right? So that'd be alpha 1, alpha 2, alpha 3. Or that correspond to 7, right? Or could be that. So that'd be alpha 1, alpha 2, and no alpha 3 because it's nullable. Okay? And then let me just do one more, and then I'm going to ask you something. So now, this one here, so that means that corresponds to 5, alpha 1, and also alpha 3, right? So now go all the way to, so now, eventually, how many production rules should we get? Should we get 8 or something less than 8? Andres.
7, because when they're all not there, then it's
Aha! Why can we not talk about, why can we not include a case? So basically Andres is suggesting, if we go pattern like this, right? When we talk about 0, 0, 0, right? Everything else is quite straightforward to include, but now should we include this particular case? You said no. Why not? Yeah, in that case, we are basically introducing epsilon production, which is our goal to get rid of, right? Okay, so now go all the way to, you might have basically just epsilon, but this is something you don't want to include. Okay, that is a very quick intuition for you for each individual step. Let's do one example. There's a grammar here. Okay, how can we derive a grammar that will get rid of all the epsilon productions? To help you quickly, what are the nullable variables? Seems to be all of them, right? Agree? Okay. Well, actually, for different reasons, right? A directly produce epsilon. B directly produce epsilon. And then S got A and B, they're both nullable, right? Okay, just remember. Okay, so now, how can we then do it? Okay, we can do that. Actually, since we're doing this manually, right, it doesn't matter. So whichever way you feel comfortable. Why don't we start with S? Let's say we'll start order. S over here, first of all, we definitely don't consider 0, 0 case, right? Either it can be A, or it can be B, or it can be AB. Agree? No epsilon for sure, okay? Now, what about for A? So now, it can be, well, AA over here, A is also nullable, right? Either you say AA, okay, include this particular A. So now, do you have to say to include this particular A also AA? Not really, right? It's kind of redundant, right? They are just the same, okay? So you don't need that. Okay, just to show you the derivation step. Okay, after this, also AA, two instances. Yes. Thank you. Like that. Yes. And no epsilon for sure. That's the purpose. Okay, similar. B produces BB and B, BB, and also B. Okay, like that. Question.
Didn't you say the algorithm was for if the epsilon is not in the language, but here it is in the language?
Aha. So now, yes. Let's get this concern well addressed. Again, it depends on what you really want, right? When you do the transformation. Yes. For this particular grammar, let's call it maybe G1, for example. First of all, epsilon is a member of the language of G1. We agree. Okay, good. So now, here, epsilon, since there's no epsilon production, it's not a member of the language of, or let's call this G2. Okay. Okay. Apparently, if you want to say strictly speaking, G1 is not equivalent to G2 because epsilon is in one but not another. So now, for you to actually to do such transformation, you want to know to yourself whether epsilon should be included or not. If it's okay to exclude epsilon in a new grammar, then you can definitely do it. It's up to your requirements. If you don't believe epsilon should be excluded, you may have some special case, maybe, just outside the grammar. Yeah.
But the claim is for this excluding epsilon, there is no epsilon.
excluding epsilon, they will be equivalent. Yes, correct. Yes. The only witness that will make G1 not equivalent to G2 is the epsilon string. Yes, correct.
How about increasing the size of the grammar exponentially when you use epsilon?
Sorry, say it again.
So you're increasing the size of the grammar exponentially when you remove the epsilon. So the question is it worth it at this point?
I would say, you know what? Since we are not really talking about exactly how to minimize the number of variables in your context-free grammar, I would say for the purpose of this course, that's fine. Yeah, just think about what you really want to do. Yeah, if you really want to remove epsilon, just go ahead, just remove them. Yeah. Okay, I noticed that I'm running out of time, right? Okay, I'll stop here, and then before I'm gonna give you back the quiz paper. Bear with me. Before Wednesday, try to trace the algorithm for the top-down parsing and also removing the left recursion. We'll revisit them quickly. I'll let you struggle a little bit for a couple of days.